Okay. Hello, everybody. I'm going to try to explain this recent Codeforces Div 3 contest with my friend here.
Yep, we're gonna do round 1107.
Okay, first question, divide and conquer. So it gives you two positive integers, and then you're supposed to check if you can choose a positive integer z that's such that z divides x, and then let x be the result of x divided by z. Okay, so we have x and y, and then x is being divided by z, and you want this to be equal to y, right? Yes, make x exactly equal to y. All right, so what do we notice? Clearly, z, you want z to be equal to x over y.
Yeah.
And since you know what x and y already are, so basically all you have to check is if x is divisible by y, then z exists, and that's it. And
Yeah.
then
Because like if x isn't divisible by y, then like no matter what you divide x by, you can never hit y.
yeah, and everything's an integer. So basically you
Yeah.
just check if x mod y is 0, and this is yes, right? Else no.
Yep.
Yay, we're done. Okay. Does this keep expanding the screen or not? All right, whatever. Next question. Good times, good times. So once again, you're going to be given only an integer x. And notice that it's strictly less than 10 to the 18th, 10 to the 8th, which means it only is going to be 7 digits long maximum. And then when you select y, it's it's less than or equal 10 to the ninth, so it means it can be up to 8 digits long. I mean, actually, technically 9 digits long, so it can reach all the numbers that are 8 digits long. Okay,
Yeah.
so that's that. So we got x and y. That's a 2. So here, what we begin to notice is you would like y to be equal to 1, but unfortunately, the problem is toxic and it forces y to be greater than or equal to 2. So why do we want y equal to 1? So first, you already know x is good, which means it only has it's made out of two distinct digits. So of course, when you multiply x by y, when y is 1, you would just get x times 1, which equals x. And since x was good to begin with, the result x times y, which equals x, is also going to be good. So we're happy, right? This is what we want. However,
Yep.
we know that y has to be greater than 2, so it kind of doesn't work. And then you get a hint from the test cases. So suppose like x is 8, and then you choose y to be 11. This multiplication results in 88, which is good because you have two eights.
That's a really good hint. Yeah.
Yeah, so like this is the hint that they give us, right? And then you check 73, and then what you see is if you do 73 times 11, you're gonna get. I actually can't do this off the top of my head. This is 3, 0, and then 1, and then it's like, shoot.
That's just designed to throw you off.
Yeah, wait, actually, like, wait, what's 73 times 11?
73 times 11, that would
Sorry.
be 803? No.
Yeah, I did my calculator. It is
803.
803. So what you realize
803.
is this doesn't work. This is not good. This is bad. So one construction that you might think about doing is you know that if x has these two distinct digits and you have to multiply by something greater than 1, so like the number has to increase. Then you might want to think about a construction like how can you make maybe something that still contains both of these digits, 7 and 3, but it only contains these two distinct digits. So then you might want to try and convert 7.3 into something like 7.373. And then you notice that you have to first multiply this 7.3 by 100, and then you add on this second 7.3, and that's like multiplied by 1. So then you
Mm-hmm.
realize you're multiplying by 101, and this happens to only have two distinct digits as well. So this actually works out. So you choose y equal to 101. And then by that same logic, you can convert this 299 into a into 299,299. That's 299,299
Mm-hmm.
by multiplying by 1,001. The same idea, right? This first 299 gets shifted. I mean, gets multiplied by 1,000, so it has three zeros behind, and you just add on this 299. So overall, if x has, what is it, d digits, then you want to multiply, then you want to let y be 10 to the power of d plus 1. And this is always going to be some number in the form of 10001. And this is going to work. And that's the answer to B.
Yep. Um,
Should we move on?
let's move on. Yeah.
Okay, now we're on to C.
Problem C.
Problem C, remove. How do you pronounce that?
RemovevomeR. That's a
Yes, that's
palindrome.
better.
Because the problem's about palindromes.
Okay, do you want to just read off the problem?
Yeah, okay. So for problem C, you have like a binary string consisting of characters 0 and 1, and in an operation, in like a single operation, you have to choose a substring that's a palindrome of length at least 2, and you can delete exactly one character from that chosen substring, and then like everything else like in the string, including what was left in that substring, gets glued back together. So you don't care about the number of operations you want to do, like you have to do. All that matters is just reducing like the string as far down as possible. So,
Okay, I guess I'll just have to take over from here because I have the notes. All right,
okay, yeah.
so how about we just go over the examples just to gain a little bit of intuition? So four zeros, right? Um, well, you can first notice that these two zeros are a palindrome, and you can just remove one of these guys. Say that guy gets cut off, and then you cut off this guy, and then you cut off this guy. You're left with 1 0, which has a length of 1. So you output 1. Bam. Okay, next we have 110, and the only palindrome here is 1 1. So you can cut out this 1, and you're just left with a length of 2, final length of 2. Next we got 110011. And then here, let's say we cut out this 1, and then you're left with this, and then cut out this 0. Sorry. You select these two. That's these two ones, that's a palindrome. You select these two zeros, that's a palindrome. And then we got 101. Say we select the 101, which is a palindrome, cut the 0, and then you have 1 1 left, and then cut this guy, and then 1 1, cut that guy, and you're left with 1 once again. And then here in this case, you got 101100. Say you take this 1 1, you cut it out, and then take this 0 0 and cut it out. Then we got 1010, and then this 101, cut the 0. These two ones, cut this guy. Suddenly we are left with 1010. And then once I cut out this 0, we have 110. I cut out this guy, and then I have a length of 2 left. I cut out the 0, right? And the problem
Yeah,
is if you cut out this 0, what happens is you're left with 110. But then in the previous case, we know that 110 is going to eventually result in 10, which is length 2.
cut the one on
However,
the
we can
left.
do
Cut the
better than
left
this,
one. Yeah,
right? You can do better. Instead of cutting the 0, what if we cut the 1, right? Now we have 010. This is good because now I can cut out the 1. And then we get 1. We get a final 0, which has length 1. So this is good.
exactly.
So this is 2, which is not good, and this is 1, which is good. So what do we notice here? Well, the first observation I'm going to make is if I have two zeros, I can always reduce this into 1 0. And by that logic, any block of in zeros I can reduce to a single zero. And then
Yeah.
same thing with two ones, I can make one one. I can get rid of one of the ones. And then any length block, I mean any however long block of ones I can make into a single one. So what this means is you're always going to be able to reduce any binary string they give you into either 1010 repeating or 0101 repeating. So let's just let's just say, I mean, I'm just going to go through this first case because the second case is very similar. So
Yeah.
let's just say we have a single one. This has length 1. If I have 10, this has length 2. If I have 101, we know we can reduce this by just first cutting out the 0 and then cutting off one of the ones. This is going to result in a length of 1. And then 1010, we just did this. You cut out the, instead of cutting out the 0, you cut out the 1 first, and then you're left with 010, and then you just cut the 1, and then bam, has length 1. And then let's just go one more time. 10101. So you can first cut out the 0, and then you would have, okay, maybe not like this. So say we first cut out the 0, now I have 1101. And then we can cut this 0 and make 111. And then we can cut this down to 1. Bam. So this is length 1. So what do you notice?
So something that you can kind of notice here is that like your answer, like it's always either going to be one or two. And if you look at like the sample input in the problem as well, you can kind of guess that maybe like the worst possible answer is two. And like when we like saw the two, like in like the examples that you wrote out, we got the two when there were only two blocks. Like if you have more than two blocks, you can always reduce it to like three blocks, and then those three blocks can always be reduced to a single number. S- So the only case where your answer is ever two is if you only have two, like if you only have two blocks in your binary string.
Yeah, so basically you can just ignore all the duplicates and then you just take the length of this final
Hmm.
string which only alternates with length 1. And then if it has length 2, you output 2, and all other cases you just output 1. All right,
Yep.
that's problem C. Now let's go on to problem D.
This was an interesting one.
Yeah, this was an interesting one. So we're given
Hmm.
two arrays, and the goal is to make array A equal to array B by performing this operation any number of times. And yeah, let's just take a look at the second example. 1, 4, 5, 2, and 1, 5, 4, 3. So the operation allows you to select any starting index and start adding 1 to that element at position L, and then the next element is -1, and then you do +1, and then you do -1. So since you can select R to end anywhere you want, what we notice is that whenever AI is smaller than BI, you can just force AI to be equal to BI. So in the simplest case, if you have something like 1, 5, you can just do this 4 times and then just make this 5, 5. Easy. But
Hmm.
then on the contrary, if you have something like 6, 5, and that's it, you have no chance of doing anything against this 6. It's already too big. And there's no way to make it smaller because you can't select L equal to -1, right?
Yeah.
So to solve this first test case, you'll be like, okay, well, this 2, 3, that's fine. I can just increase this by 1, right? That's all good. Okay.
Hmm.
So if I want to decrease somebody by 1, what we'll notice is if I want to decrease somebody by 1, I have to increase the person to the left by 1. So at the cost of making this guy a 4, I have to promote this guy to a 5. And this might be bad, of course, because suppose this,
Yeah.
you can't, suppose like it's already bigger. But then, yeah, you basically are just doing this. And then That's fine. You demote this guy to a 4 at the cost of promoting him the guy to the left to a 5. And this ends up working out 1 5 4 3 and then 1 5 4 3. It's fine. So then what we notice is, since in order to decrease somebody by 1, we have to increase the guy to his left by 1. This motivates us to loop through the arrays in reverse. So yeah, this is, for example, here 9 8, nothing you can do. Okay, this 6 7 one is pretty obvious, right? Because for each 7, you can just decrease it by 1 at the cost of increasing the 6 to its left.
Exactly.
So here's the first interesting test case. So we got the 9 8 7 6 5
Mm-hmm.
4 3 2 1, and then 9 9 8 2 4 4 3 5 3. Okay, so first I check this. So you have 1 and 3, which is which you can just promote this to a 3 easily by applying the operation with L at index 9, assuming we're one index. Here, once again, you can just add 3. You can make this a 3. Make this a 5.
Mm-hmm.
This is already good. This is good. And here's the first index where we see AI is greater than BI. So then we have to decrease him. And then a strategy is you can just count the current cost. So in order to decrease this 5 by 1, we have to increase this side by 1. So now this is going to incur a cost of 1. So say we have cost of 1 here. And then the 6 and 2, say we have to incur a cost of 4. And then the 7 and 8. So now notice, instead of automatically promoting this 7 and 8, so promoting the 7, you can think about this, right? You already know that you have like another 5 cost here. So this 7 is actually a 12, right? So now
Mm-hmm.
pretend this 7 is a 12 now. And then what we realize is this 7 is basically, well, you have 12, but we only want 8. So you actually only want to subtract 4 here.
Mm-hmm.
But but basically this since it's smaller, we don't actually have to continue like this cost pushing this cost of 5 downwards. We only we only need to continue with the cost being 4 because this 8 is going
Yeah.
to absorb 1 cost. That's what I wanted to say.
Mm-hmm.
Okay, I overcomplicated that. So now if there's a time where AI is smaller than BI, it's actually going to absorb some of the cost. So now we
Mm-hmm.
have a cost of 4 going here. And then once again, this 8 and 9, it's going to absorb the cost, a cost of 1. And then finally, you basically are just simulating like like the process going
Yeah.
left. It's just that simple. And now you have
Pretty
12 and
much.
9. And then at the very end, you just have to check if the final A0 is just less than or equal to B0.
Yeah. I
And
did
then
like a
how
similar thing,
and then once you
except I
check the
went from left
cost,
to right instead. Yeah.
wait, -1 again here. The cost is 3. So originally the A0
Mhm.
was 9, but then you just add 3 to make it 12, and then you just check at the end.
Yeah.
This.
I kind of did something similar, except I went from left to right instead. And like I'd like add as much as possible to the current element and then subtract that same amount from the one to its right. And if you ever hit a point where like the value at A is greater than the value at B, then like it's impossible to make it work.
Yeah. I don't think we need to explain. I mean, fine. Let's just explain this one. This is just very quick, right? 2 1 1.
Yeah.
So once again, this is gonna make a cost of 1, and then this is not gonna change anything, and you add the 1 to the final element, and then that's 2 2, and that's fine, right? Because A0 less than B0.
Mhm.
Okay, now I'll hand it over to you to explain the final problem, E.
Sounds good. Okay, let me share my screen.
Mm-hmm.
We'll probably just do this on Discord, I guess.
Yep.
Okay. Uh, can you see my screen?
Yes.
Yes? Okay, awesome. So problem E. This was an interesting problem. Um, how do we like think about this problem, I guess? So first of all, let me like explain what this let me explain briefly explain like the problem statement. You're given a tree with n vertices, and a tree, like as we all know from basic graph theory, it's connected, it's not directed, and it doesn't have any cycles. So you're given a tree with n vertices, and each vertex has like an integer value, and you can define p of u comma v as the product of the values written on the vertices lying on the unique simple path from u to v. And a cool property about trees that we know from graph theory is that there's always one unique simple path from u to v, from like one node to another node without visiting like the same node multiple times. And now we call a triple of three distinct vertices good if and only if the product of the values on the paths from all three pairs of nodes is a perfect square. And our goal is to determine the number of good unordered triplets in the given tree. So it's unordered, so that's cool, I guess. And now let's think about how we want to do this problem. Let's look at the first sample test case. So I'm gonna root the tree at like node one. It doesn't really matter where you root it. I'm just gonna root it to give us like an idea of the structure of the tree. You can have something like this. This is what the graph of the tree in the first test case will look like. And I'll use a different color for like the integer values on those vertices, like 1, 1, 1, 1, 1. And the problem gives us like all, the problem tells us like all like unordered triplets of three distinct vertices that are good for the first one. And the problem essentially tells you that any unordered triplet in this graph is good since the like no matter what path you take on this graph, it's always going to be one. So your expression like p of, or let me use text for this. Your expression p of u comma v times p of u comma w times p of v comma w will always equal 1 times 1 times 1, which is a perfect square. It's like we're chilling with this example. That's cool. Um, in general, though, like the values of a can be at most 10 to the sixth, so you could be dealing with some really like interesting stuff. So how do we go about like actually finding the number of good triplets in like a tree for like a more harder for like a harder version of this problem? So first of all, one idea we can think about is like we can every every unordered every triplet of three distinct vertices, you can always like find its least common ancestor, which is like the the closest node like above it in in like a rooted tree that's a common ancestor for all three nodes. So let's draw
And let
like
me ask you a
a
question.
bigger.
So why are we doing the least common ancestor, right? We know that there's in basically in choose three possible pairs, right? Wait, no, in
Yeah.
choose three, and then all the different permutations.
Hmm.
Yeah, so like that's like way too many, right? Like because there's six permutations. Like all six
So
would
the
count, right?
mhm.
So then overall you
So
would have like way too many like if you're just trying to brute force like it just you would have way too many like
mhm.
different checks that you have to make.
So that's like a great point, but or that's a great point. The reason why like I thought to think about the least common ancestor here is because that can kind of help you think about like the length of like paths in a tree. Because another fact about graph theory is that the distance between two nodes in a tree is the distance from both of those nodes to their least common ancestor added up together. So for example, like the distance between this node over here and this node over here involves climbing up to their least common ancestor, which is this node over here. And if you have something like this, where one node is directly an ancestor of the other one, then this node at the top is the least common ancestor, and then their paths both involve the nodes going up to hit that LCA and then meeting up. So since we're talking about like the unique simple path from U to V, that prompted me to think about considering like the LCA of like your triplet of nodes and seeing if we can do anything interesting about that. And if we find a way to handle each individual LCA super quickly, then our time complexity is still O of n, since there's only n possible nodes that could be the LCA, like for your triplets. So let's think about let's like pick some three random vertices, U, V, and W, whose LCA is like, let's say the root for now. That might be good for this example. So clearly, like there's three different subtrees for the three children of the root node. Clearly, if all three nodes were in a subtree of like one of the children of the root, like these three nodes, for example, then their LCA wouldn't actually be the root. It would be one of the children of the root. So we do not want like our triplet of vertices to all be in the same um in like
Subtree?
the same subtree rooted by one of like the root's children.
Uh-huh.
So we want to like spread the three vertices U, V, and W across like these different like across the different subtrees of like the children of like the LCA that we're considering. So we have a couple cases. Case one is all three of them are in different different subtrees, right? It's like let's say this is node one, this is node two, and this is node three. What happens when you like consider like multiplying like the paths of all of these nodes out? Let's say this number has an A, the value of of this node's a B, it's a C here, a D here, and an E here, and this node was an F. Let's assume like it goes like that. The distance from the first two between the first two nodes is going to be, I'll use text for this because it'll make it easier. A times B times C times D, because you go from A to B, B to C, and then C to D down from the LCA. Then you have from the first node, the distance from the first node to the third node is A times B times C times E. And the distance between this, or the product path, the path of the product of like the path of values between like the second and third nodes in this triple will be D times C times E. So do you notice anything about like this like total product? Because like all of these values multiplied together will be defined as will be like the product of like all the pairs of
Ooh,
like
I
the
do
products on
notice
this.
something. It seems like
What do you notice?
C appears three times, while A, B, D, and E only appear twice.
Exactly. So since A appears twice, A squared, that's a perfect square. So essentially this product is a perfect square multiplied by it's like some perfect square multiplied by C. Since C appears three times, so you can assign two of those appearances to be like a perfect part of the perfect square. So you're left with a perfect square times C. So notice that like all we need to do is check to make sure like this value is a perfect square. And if we know that this value is a perfect square, then like all triplets that are spread across different like subtrees, we know all of those triples will be good. So that's one case. Now, oh boy, we have a ton more cases to go. So I'm I'm gonna like redraw this graph really quick, and I'll also like copy paste it because there's a couple more cases you have to consider. There's the second case that I mentioned earlier. So earlier I was talking about how like all three nodes have to be like spread across different subtrees of the current LCA that you're considering. What happens if two of those nodes are in the same subtree and one of them is in a different one? Let me, or I'm gonna copy paste that first. Now, let me draw our three subtrees again. And what if we have two nodes over here, for example, and then one node over here? If you multiply out the paths and stuff, what you're actually gonna find is that the value that repeats like three times is actually going to be this value over here. I'm going to mark it in black. This is the value that's going to repeat multiple times. There's a ton of cases here, so I honestly don't want to go through like multiplying everything out to show you. But every node that appears in that final product will appear twice, except for this node that like I pointed to with a black arrow, that's gonna appear three times. So that's kind of what we need to identify. For every LCA, or for like the current node we're considering, we need to identify like all nodes inside it who like whose values work and who have like at least two children. And then for each of those, we can just pick a third node wherever we want. And that will be like our answer in this case. What's the next case? Our next case is if, so in all of these cases so far, we've assumed that like the LCA isn't part of the triple. We're still going to do that because there is actually like a third case I haven't mentioned yet from that, but keep that in mind. So going back to this, what if like that second node we picked wasn't this one, but this node instead? So one of the nodes like we picked is directly an ancestor of the other node, like in that shared subtree. In this case, it turns out that what we're gonna have is that that node over here, like the same node, like that ancestor over there, that's also gonna be the one that appears three times. So that's also something we're gonna need to check. And other than that, like it's like a it's basically the same as the first case, like the case I mentioned before, except this time instead of like those the two nodes I mentioned, not like having a third different ancestor in that subtree, one of them is directly going to be the ancestor of like the other. So that's a case we're going to have to consider too. We now let's consider the cases where like our LCA is actually part of the triple. So we're going to highlight this node is going to be part of the triple. So then what are some cases we have? Like obviously like at this point literally any other two vertices like in the subtree of the current node can be picked since their LCA is always going to be guaranteed to be like the root. Let's assume for now that they're in two different subtrees though. If they're in two different subtrees, it turns out that this like the LCA root that we have over here, this is the value that's going to appear three times. So this is the value we need to check to make sure it's a perfect square. And there's a couple more cases. So what if we have something like, or let me, do I not have the old one copy pasted? That's unfortunate. Okay, we'll use this though. So in that case, like the two other nodes we chose, they're in different subtrees of like the LCA. Then we also have the case where one of those nodes is like the ancestor of the other. So I'm gonna put an X out here and draw like that node over here. And in this case, instead of like the value that repeats twice being like the LCA, it's actually gonna be the ancestor of like the the two like um the two other nodes inside that same subtree. And the last case we need to consider, it's kind of like the analog to this case over here. Pretty much, let me copy paste one more time. Instead of like this stuff there, we just pick like the two other nodes like belonging in the same subtree, the same like subtree of the LCA. And in this case, the value that's going to repeat three times is going to be the LCA of these two smaller nodes. In the same way that like in this case over here, the value that repeats three times is going to be the LCA of like those two common nodes over there. So this was quite a mouthful, and implementing this is it's not like exactly the most fun experience. There's probably much better ways to implement this though, but you can kind of like reduce everything down to these six cases and just implement from there. So now the question is, how do you actually implement all of these like different cases, right? So how do you do that? What you can do is you can like you can compute a bunch of information about the tree using depth first search. You can compute like the size of like the subtree like rooted at every single node. What you can also do is to handle this first case over here, you can you can use DP to count like the number of pairs of three nodes coming from different subtrees, such that like the number of triples of like three different nodes from different subtrees. You can kind of do this by like going through the sizes of the subtrees. This subtree has a size of 3, this subtree has a size of 4, this subtree has a size of 4 as well. And you can let like dp of I of j be the number of ways considering the first I subtrees with j elements, with j nodes in like the tuple. So j goes from 1 to 3, and I goes from like 1 all the way to like the number of subtrees in this case. And you can pretty easily compute this sum by noting that the transitions are as follows. Like dpi of 0 is just equal to the size of like the ith subtree, so it's just this. dpi of 1 is equal to the size of the current subtree multiplied by dp 0 of 0 plus dp of 1 of 0 all the way to dp of I minus 1 of 0. And then dpi of 2, it's the same kind of formulation as dpi of 1, except you instead like use like the pairs to build like the triple. So you get something like this. 0, 1 plus dp 1 of 1 plus dp of I minus 1, 1. And you can just add up the sum of dp I of 3 for all I from 1 to like the number of subtrees in this case, and that gets you the answer in this case for the total number of triples that share like a common LCA of your current node, and they're all in different subtrees of the graph. Phew, that was a mouthful. So to handle the second case, we can also compute a second type of DP that stores for every single like node the total sums of all pairs of nodes that are who share like a common ancestor that's in like your current subtree, and like the value at that current subtree is a perfect square. So for example, like the DP at this value here would be 1, since it's rooted at a value at a node whose value like is a perfect square, assuming that triple works, and it has two children, so you can make that work. Two children in two different like subtrees. So you just keep building this DP as you go, like through your depth first search over this tree. And then your answer is essentially you just pick one of these subtrees to give you like one single number, and then you sum the DP the DP values over all the other subtrees and just multiply that together. So as an example, this is a different DP formulation, by the way. You would get something like DP of, or like answer plus equals, or like the answer at the current LCA would like plus equal size of like the ith subtree multiplied by the sum of the DP values of all the other subtrees. And you can implement this in like O of n time by also like maintaining the sum of the DPs of all the children's subtrees. And then for like the current like subtree you're iterating on for to get like size of I, you subtract like its DP value from that total sum. So you can get this in O of n too. This third case, you can maintain another DP for this. And this DP formulation it's like a bit simpler. You base like this DP of I like essentially stores the number of pairs of nodes such that one is the ancestor of the other, and that ancestor node has a value that's a perfect square. This also isn't too bad to maintain as you like do your DFS. And then the answer, like in this case, would just be you iterate over like you brute force. It's the same as like the earlier case, except you use like this different DP formulation instead. So you do sum of the DP of the roots of all the other child subtrees. And then we have three more cases, but these cases are like much easier to think about. For this one, this is the exact same as case one I mentioned, except you only need to worry about like making sure you have two numbers that are in different subtrees. So you can use like the same formulation as like this one over here. It's like case one, except like same DP formulation as case one, except your two like except like your value your J it's bounded by like 1 to 2 instead of 1 to 3 as in case one. Since we don't need to worry about finding the third node in here since we've already fixed our third node to be like the LCA that we're currently on. Then this case over here, this is similar to case three, since this is also dealing with like finding like a pair of nodes such that one is the ancestor of the other, and you can use the exact same DP formulation. And in this case, like the answer is even simpler. Like the answer of the node is just equal to the sum of the DP values of all the subtrees, all the child subtrees, and you and that's literally you just like add up the contributions of everything. And then once you're done, you also like update like all the DP formulations as you move up as well. And then the final case is this one kind of corresponds to case two, I think, where you have like two in one like child one of this in like one subtree, but like they aren't ancestors of the other. And then you use the exact same DP formulation as the one for that case, except you add up all the contributions instead of iterating over the third one, since your third one is already fixed as the LCA. And if you like implement all of this correctly, it it should AC. And yeah, this problem was a bit to think about. It's you on it like you like the key insight here is you kind of like realize that every triple you can group like every triple based off like its LCA and then just iterate off the LCA. And then for each of those, there's only like a couple possible like cases for like the orientation of the three nodes. And then for each of those cases, there's like a relatively like straightforward DP formulation that works. And you can also reuse a lot of those DP formulations over all the cases, since there's a lot of similar structures. For example, like two nodes, what like being part of like your tuple with one being the ancestor of the other. And in that case, you also want that ancestor, like the value in the array A to be a perfect square at that value. So another implementation thing we have to do is also like for each index and like for each element in the array A, we also need to check if it's a perfect square or not. You can use like the square root function and then check if that value squared actually equals like your the value at that position. And that can tell you whether like a number is a perfect square or not like relatively quickly. So that's a high level overview of the problem. Each implementing each of like the individual components isn't too terrible. And yeah, this is a fun problem to think about. And I will hand it over to my partner. Unless
Yeah.
like if there's any other like areas like you think I could probably like explain more, I can do that as well.
Yeah, I think you explained this pretty well. I was like
hmm
wondering if there's any other way to do it, but I haven't thought of that yet.
I
Yeah.
think you can probably simplify the solution a lot too, because I feel like you can probably handle the cases where like you have like these two nodes that like where one is like the ancestor of the other, as well as this case where like the two nodes like aren't ancestors of the other, but in like both of those cases they're still part of the same subtree. I feel like you can probably find a way to combine both of those since they're handled very similarly. Would not surprise me if you can also get this down to like 5 or 4 cases instead of 6.
Yeah, that's tough. All right, well, that'll be all for today's explanation. Thank you very much for watching.
Yeah, thank you.